Bismillahirrahmanirrahim. So we were talking about the chapter 2 number systems. We have defined the number line. We have talked about different numbers, and then we talked about these rules of real numbers. Now we will talk about the topic rationals and irrationals. Okay. There is a proposition 2.1 which says that between any two rationals there is another rational. This says that if you have two rational numbers, there is another rational number between them. Let's prove this. Let's prove this. The proof, we say that let R and S be two different rationals. Let R and S be two different rationals. Okay. We say R is the larger. So say R is the larger. So say R is greater than S. We claim that the real number, now we claim that the real number 1/2 of R plus S is a rational lying between R and S. And to see this, observe that one half of R is greater than 1/2 of S, then R over half of R plus half of S is greater than half of S plus half of S again, and then half of R plus S is greater than S. And likewise, half of R is greater than half of S, then half of R plus half of R again is also greater than half of S plus half of R. Then we can say R is greater than the half of R plus S. Thus, half of R plus S lies between R and S. Finally, it is rational since if R is M over N and S is P over Q, then half of R plus S is going to be MQ plus NP over 2NP. So this proof shows there is a rational number between two rational numbers. Now, despite its innocent statement and quick proof, this is a rather significant result. For example, it implies that in contrast to the integers, there is no smallest positive rational, since for any positive rational x, there is a smaller positive rational. For example, 1/2 of x. Likewise, given any rational, there is no next rational up. The proposition also shows that the rationals cannot be represented completely by dots on the real line, since between any two dots, there would have to be another dot. So that's the theory. The proposition also raises a profound question. The rationals are dense on the real line. Should be noted. The rationals are dense on the real line. And in topology, you will learn that what do you mean by a dense in this sense? But they do, but do they in fact fill out the whole line? Like, is it only the real, like whole numbers as the real numbers, and then integers, negative ones, and then these rationals, do they fill up the line? The answer is no. In other words, is every real number a rational number? The answer is again no. As we shall now demonstrate, first we need the following proposition, which is not quite as obvious as this looks. So let's present that proposition. Two point two says that there is a real number alpha such that alpha square is 2. Remember, there is a real number alpha such that alpha square is 2. And to prove that, we draw a square, of side 1. Let's draw that. Hope it looks like a square. Okay. Then we say one here, there is a diagonal and we call it alpha. Okay. Now we know that alpha be the length of a diagonal of the square. So let alpha be the length of a diagonal of the square. Okay. Then by Pythagorean theorem, Pythagoras theorem, we have alpha square is 2. Now, for the real number alpha, we adopt the usual notation alpha is equals to under root 2. So by proposition 2.2, we say alpha is under root 2. And then we have squared it. And then got the alpha square is 2. But there is a very famous proposition, and maybe many don't know about it, or like believe that it is different. So it says that under root 2 is not rational. Now we'll prove this by contradiction. By contradiction, we assume that under root 2 is rational. This means that there are integers. This means that there are integers m comma n in the integers such that under root 2 is m over n. Okay, now take m over n to be in lowest terms, like it cannot be more factorized, and they do not have any common factor except 1 terms, and square the above equation and square, let's say we name it star square star both sides. We will get 2 is m square over n square. Hence, m square is 2n square. Okay. And if m was odd, if m was odd, then m square would be odd. Did it in the previous chapter. But m square is actually 2 into n square. From here is clearly even. So this cannot be true or be the case. Therefore, m is even. M is even. Hence, we can write m is 2k, where k is some integer. Then m square is actually equals to 4k square, which is 2n square. Consequently, n square is 2k square. So n square is even, and this means n is even. N is even. Now we have shown that both m and n are even. However, this means that the fraction is not in choice terms. So we have shown that m and n are even. This means that m over n is not in its lowest terms, which is a contradiction. So this is a contradiction. Therefore, the root 2 is not rational. This is the proof. Perfect. Now the following slightly more complicated geometrical argument than that given in proposition 2.2 for the number whose square is 2 shows the existence of the real number under root n for any positive integer n. So let's say we have a circle and then we have triangle in it. Okay, let's name these C, B, A, D, 1, and right. So from there, we are going to say that the real number under root n for any positive integer n exists. Now, x in this figure, we draw a circle with the diameter AB. So the diameter is AB, and with a point D marked on the mark, so that AD is n. So let's say AD is n and DB is 1. Now we'll use the Pythagoras theorem in the right angle triangle ABCD, BCD, and ABC to show that the length of CD has a square equal to n, and hence CD is going to be under root n. The length of CD is the square equals to n, so you can use the Pythagoras theorem to find this, and then you will conclude that CD is under root n. Now, that you can do by using the Pythagoras theorem. And from here, we have found that under root 2 is not irrational, it's not rational. Then what we call it? So a real number, a real number that is not rational is called an irrational. Thus, under root 2 is irrational by proposition 2.3. And by our next proposition, we will be able to construct more irrational numbers. So let's do that. We have proposition 2.4 says that let A be a rational number and B an irrational, and one is, then their sum is irrational. Two, if A is non-zero, then their product is also irrational. And we can prove this. So for one, we prove by contradiction. And suppose A plus B is rational, say A plus B can be written as M over N. Then writing the rational A as P over Q we have. So let's say A is P over Q. We have B is equals to M over N minus A, which is M over N minus P over Q. However, the right hand side is rational, whereas B is given to be irrational. So this is a contradiction. So a rational cannot be equals to the rational. The right hand side is rational, but B is irrational. So this is a contradiction. Hence, A plus B is irrational. And you can prove part 2 as part 1. So let's just write similar to part 1. Example. The proposition shows that, for example, 1 plus under root 2 and minus 5 under root 2 are rationals. So indeed, R plus S under root 2 is irrational. For R and S in rationals with S not equals to 0. Note that there exist many further irrationals, but not of this form. For instance, under root 3 is irrational, and there are no rationals R and S such that under root 3 is equals to R plus S into under root 2. Thus, there are many irrationals in some sense. The next result shows that, like the rationals, the irrationals are densely packed on the real line. So let's talk about that result. So that is proposition 2.5. That proposition shows that between any two real numbers, there is an irrational. You can prove this. We give the proof. Let A and B two rationals, two real numbers, and say A is smaller than B. Choose a positive integer n that is larger than the real number. So choose a positive integer n which is larger than the real number. Okay, larger than under root 2 over b minus a. This is integer and this is real. Okay, then under root 2 over n is less than b minus a. So if a is rational, then by proposition 2.4, a plus under root 2 over n is irrational. So it also lies between a and b. And if a is irrational, then a plus 1/2 or 1 over n is irrational. And lies between a and b. So between any two real numbers, there is an irrational number. So we can say the irrationals are dense in what the statement we made here, dense in real numbers, dense in or on the real line, dense on the real line. Perfect. And this was the introduction and somehow the concept of rationals and irrationals. I'll see you in the next lecture in which we will talk about some exercises of this chapter.